Got a very important definition up here on the board. We say a vector function r of t is continuous at a value a if the limit as t approaches a of r of t is equal to r of a. Now that's the formal mathematical definition. I could ask you for that at some point. That makes a great short answer question. I like to remember this by just saying nothing weird happens. The limit describes what I expect. This is what I expect to get at a based on the nearby behavior. If I look at t-values close to a, they're going to lead me to expect something. That's what I call the limit. This is what I get. So, definition of a function being continuous, the informal definition, what I get is exactly what I expect. Nothing weird happens. Okay? That's true for real valued functions. For real valued functions, I just replace the vector notation with real valued notation. It's exactly the same. If the limit is equal to the function value, that it's continuous at that particular point. Notice, in order for this to be true, a does have to be in the domain of the function, because otherwise I don't get anything. And if I don't get anything, I can't get what I was led to expect. Okay, now in practice, since we evaluate limits, which are the left side of this equation, component-wise, we're going to look for continuity component-wise as well. So r of t is continuous at a if and only if. It looks like I misspelled the word if. I'm just very excited about the letter F here. IFF actually is a mathematical symbol for if and only if. Okay. R of t is continuous at a if and only if each of its component functions is. Okay, so if the vector function is continuous at a point, then I know that each component function is continuous at its point, at that point. The way we're going to use this more is in reverse. If I know each component function is continuous at a point, then that tells me that the vector function is continuous at that point. And very often, we're concerned about functions being continuous not just at individual points, but on their domain. So r of t is continuous on its domain if it is continuous at every point in its domain. Okay, so the definition of continuity is for individual points, but then I say, well, the domain is just a whole collection of points. So if the definition is satisfied for every point in the domain, then we can say the function is continuous on its domain. Okay. Couple of important things. If I look at r of t equals cosine t, sine t, t, it's very easy to see that that's continuous everywhere. Its domain is all real numbers, and each component function is a continuous function. Okay. If I look at r of t equals 1 over t, t squared, natural log of t, that is also continuous on its domain. Now its domain is not all real numbers anymore. I can't plug in 0, and I can't plug in 0 or anything negative. So the domain is all positive numbers, okay? But this function would be continuous at all positive numbers, okay? And that means it's continuous on its domain. I could have something like r of t equals 1 over t, t squared. Okay. Now there's a gap in the domain. It's not just that I only work with positive numbers. It's everything except 0. This is still continuous on its domain. Okay. Continuous on its domain. That does not mean that it's continuous at 0, because 0 is not in the domain. So it's also not continuous at 0. Okay. That's not a contradiction because 0 isn't in the domain. Okay. So we've seen that with real valued functions as well. I can say the function 1 over t, just looking at that component function, that's continuous on its domain. It's not continuous at 0. Same thing extends to the vector function. Okay. So this notion of continuity, I get what I expect, the limit is equal to the function value. That's going to apply to any type of function that we work with. So up until this class, you've been working with functions where the input was a number and the output was a number. Now we're looking at vector functions. The input is a number, the output is a vector, which we identify with a point in n space, but the definition of continuity is the same, that the limit, what I expect, is equal to the function value, what I get.